lot the fact that a lot, chapter 8 is very important. A lot of things are made from alkenes. Therefore, it's certainly important to know how to make an alkene, since we can do so many things from an alkene, right? And the main strategies that we have to make alkenes is to eliminate. Okay. So, what do we eliminate to get an alkene?
Hydrogen.
Okay, hydrogen and something else, I'm leaving. What's the something else? From what type of molecule, what type of functional group do I need?
Halogens.
Okay, so one thing would be to have an alkyl pair, right? What is the other thing that I can eliminate? You should all know because all of you try to do this. An alcohol, right? Now, what's the difference between these two? This is my leaving group. This is a good leaving group. This is a lousy leaving group. So we need different strategies. In this case, what I need is a base. A base that will come in an E2 elimination. Take this acidic hydrogen, put these electrons here, and kick this out. Since the bromine is a good leaving group, it is willing to leave, right? And you form an alkene. So from an alkyl halide to an alkene, I'm using a base. That's sodium hydroxide. Sodium methoxide, sodium methoxide, a base. Can I use a base here to do the same type of reaction?
No.
No, because OH minus is a lousy leaving group. So first I need to convert it into a good leaving group. There's different strategies to convert this into a good leaving group. But one of the strategies is put it in acid. Because if you put it in acid, like sulfuric, something like that, this picks up hydrogen. And now, this, with a positive charge, is a good leaving group. So then we have a solvent like water, or even another molecule of my alcohol, right? Whatever it is, this weak nucleophile can then, well actually this is more likely to go here. You want to set this as primary, but anyway. Once this is converted into a good leaving group under acidic conditions, then I can form the alkene. I cannot tell you how many of you, given an alkyl halide, put an acid, or given an alcohol, put a base. They're not interchangeable. This is an elimination under basic conditions. This is an elimination under acidic conditions. And they are not interchangeable. Okay? Now, why do I want an alkene? Because then, from an alkene, I can do a variety of things. So, let's say that you have an unsymmetrical alkene. So, let's say that I have this, and I ask you to make this. How can I do that? to an alkene. I eliminate with acid and base. I form the alkene. The power of an alkene is that I can then add groups Markovnikov or anti-Markovnikov. So once I remove it, I can add it where I want it. I could from here go back to this, that would be Markovnikov. Or if I want to add this anti-Markovnikov, then I put HBr with peroxide. Right? Of course, from here, I could go this and just put HBr, that would give me the Markovnikov product. But if I wanted anti-Markovnikov, I can do that. And of course, the same would be true with an alcohol, right? If I started with this, and I wanted this, I would still need to eliminate. And of course, now it would be under acidic conditions, right? So furic acid, heat it, eliminate, and then add the OH anti-Markovnikov, which in this case would involve an hydroboration oxidation, right? So, and again, of course, if I wanted to go back this way, I could do an oxymoration evaporation, Markovnikov conditions. The point I'm trying to make is that from an alkene, I can make a myriad of things. I can make alcohols and alkyl halides, but I can make epoxides and cyclopropanes and diols and 8 gazillion different molecules. Once I get to the alkene, I've got a myriad of things that I can do. But I need to know how to get to the alkene. Right? Now, if I had the first synthesis problem that you had, and your product is this, and I'm asking, how do I get this? The first thing I always told you is look at your carbons. What is connected to what? What kind of bonds are we trying to make to which carbon, right? So in here I have this carbon and this carbon and this carbon and this carbon, right? And this other carbon over here. So, over here, my leaving group, my bromine, is connected to blue carbon. Over here, this oxygen is connected to green carbon. They're not the same carbon. I'm not going to come with a nucleophile and pretend to do an SN2 reaction here. First of all, because I cannot do an SN2 reaction that first reactor makes. I cannot. But second, because it's not the right carbon. So what do I need to do? Convert it to the alkene, and then add the bromine where I want it. So that I can then do the SN2 reaction, right? Let's get rid of this bromine and blue carbon where I don't want it, and put it on green carbon where I want it. So then I can come with the alkoxide ion and do an SN2 reaction, right? How do I get rid? How do I make the alkene? The base, right? So we put some sodium hydroxide, methoxide, ethoxide. I don't care what base, any base will do. And we have an alkene. And then I want to make this alkyl halide, which is now secondary, which can undergo an acetyl reaction. Is this a Markovnikov or anti-Markovnikov product? Anti-Markovnikov, right? The bromine is on the least substituted carbon. So anti-Markovnikov in this case means HBr with peroxides. Now I have the bromine where I want it. Now I can go ahead. Now, if I'm going to do an acetyl reaction, I need a strong nucleophile. So, not just the alcohol, but the alkoxide ion, right? So, I would need to put some sort of a base, like the sodium hydroxide, make the alkoxide ion, right? For SN2 reactions, we need strong nucleophiles, and this alkoxide ion will come, displace this, and now we have isomer. But if you refuse to ignore, to consider what is connected to what, you're never going to get the right product. You can't just ignore and say, well, it's all going to jump out of the way, and I'm going to somehow end up with what I want. Okay? All right. B, I think pretty much everybody or most people got it. You make the tosylate, because it's only one inversion. You need to not change inversion until when the cyanide ion attacks. Most people got that correct. Now, so let's look at C. By the way, did I make any carbon-carbon bonds here? No. I made a carbon-oxygen bond to connect this piece to this piece. So nowhere in here should I be looking at Grignards as a strategy, because Grignards are to make carbon bonds, not carbon oxygen. Right? In here, I am making, right? Here's this from here, and this from here. I am making a carbon-carbon bond. Now, you conclude in here that you will likely need a Grignard. You don't conclude, oh, I just dosed in some magnesium and miraculously this is all going to happen. We go back and we say, how do we make Grignards? How do we make carbon-carbon bonds that results in the formation of an alcohol? I make a Grignard from what? A halide. And my halide, to form an alcohol, needs to attack an aldehyde or ketone. I don't have either one of those things. I need to make them first. Since this has an oxygen, let's assume that this is going to be my aldehyde. Let's oxidize this to an aldehyde. Okay? To which my Grignard is going to add to form the alcohol. Right? Semi two carbons, and this oxygen, which is going to become OH. I need to make this into the alkyl halide that then I'm going to add the magnesium and form the Grignard, which will attack this aldehyde. How do I make this here? HBr. Doesn't matter Markovnikov is a completely symmetrical alkene, so it doesn't matter. Once I have the two things that I need, then I do the actual reaction, right? So I have this halide. First, I put the magnesium, form the Grignard. Second, I put the aldehyde. And third, I hydrolyze, and I end up with this product. Okay? So again, we look at the product, we look at the starting materials, we figure out what is coming from where, typically carbons, right? We look at what particular bonds we're making to join those pieces together. If that bond is a carbon-carbon bond, then let's use a strategy that makes carbon-carbon bonds, like Grignards. Then you say, okay, and how does this Grignard work? Well, I need a halide. If I'm going to make an alcohol, I need a ketonaldehyde, right? And then I start looking into making those things. But there's a process here. Okay? All right. Let's look at D. In a previous problem. So, likely, you could have just flipped the page over and see what that was about. But, let's start again. So, what is coming from where? This, right? And these three carbons are going to be these three carbons. So I'm making a carbon-carbon bond. Okay. What strategy am I using here to make a carbon-carbon bond? I'm Grignard again. Okay. Now, we've looked at Grignards, whatever they happen to be, attacking some sort of a ketone, and that gives you an alcohol at the end of the day, right? But we don't have an OH here, so that's not that. But Grignards can also attack, for example, oxides. And now you would have two carbons in between whatever is coming from the Grignard and the OH, right? One carbon in here, two carbons in here, and then the OH. So in here, between this carbon from the Grignard and this OH, there is two carbons. So chances are we're using this strategy, right? Okay, now this piece is going to be the Grignard, that I'm going to add to this epoxy. Okay. This piece is going to be the gradient. What do we make gradients from? And how do I convert this into an alkyl halide?
Substitution.
I put HBr. Markovnikov or anti-Markovnikov? Anti-Markovnikov. So in addition to the HBr, I'm going to toss some peroxides. Right? So from this, I'm going to put some HBr with peroxides, which will give me the bromine here. So that then right, this is going to be the carbon that's going to add to epoxy. Right. Okay. How do I make from an alkene an epoxide? A peroxy acid like metachloroperoxybenzoic acid or something along those lines. And then you would have, now I want the OH on the front, so that when this opens, it stays on the front. Okay. So now all I need to do is, from here, I put magnesium to mix the Grignard to, I add this here, H3O plus.
Why do we have the acid?
Because you end up with an alkoxide ion. Grignards are highly basic. So as long as you're under those conditions with a strong base, you're going to have O minus here. If I want an OH, then once the reaction is completed, I toss the whole thing in some acidic water and then it fixes the hydrogen. Once again, you were looking at these things, looking at the bond that we're making, and figuring out your strategy from there. Okay? This is not going to go away. What is going to change is, as soon as we're done with NMR, we're going to start looking at more functional groups. Carboxylic acids. Okay, carboxylic acids are made from alcohols, which are made from alkenes. Esters. Esters are made from carboxylic acids and alcohols, which are made from alkenes, which are made from alkyl halides, which are made, no? So, and we're going to continue doing syntheses, and you need to know these strategies. You just cannot pass this course if you don't know this type of reactions. I know it seems like a myriad of things, but when you get yourself organized and you say, okay, how do we make alkenes? By elimination. Of what? An alkyl halide or an alcohol? It's pretty limited, right? How do I make carbon-carbon bonds? So hard with gradients. By the end of the semester, we may have looked at like 3 or 4 more strategies, but they're limited. Let's learn them. Okay? And of course, if I need a Grignard, I need a halide. And how do I make halides? Well, or from an alcohol. How do I make a halide from an alcohol? If I had an alcohol. PBr3, if it's a primary, secondary, or if it's a tertiary with HBr. Okay? So again, let's have those. How do we make alkyl halides? Page. How do we make alkenes? Page. What are the reactions of alkenes? Page. Okay? Keep reviewing it and writing it. And then you can answer this question.
Is it just PBr3 for all posts?
you had this alcohol, and you wanted to make this. In one step, I could add PDR3. Now I can do 2 steps. I could add acid, eliminate, and then add HBr. But why? If I can add PDR3, I did it. Right. PDR3 works for primary, secondary alcohols. If you've got a tertiary, you really need to go with HBr because this is an SN2 process, and SN2 doesn't work on tertiary. Okay? All right, so the rest you can go over yourself. If you have any questions, just let me know. Over to my office, we can go over that. But I just wanted to go through the synthesis to show you that this is pretty much what we've been doing all along. And the same strategies and the same analysis. All right, now, NMR. All right, so I told you before the exam that NMR looks at the radiating a molecule with a radio frequency. Very, very, very low energy. But enough energy that the protons in the nucleus of each atom can slip. Now, each proton, each positive charge, each negative charge for that matter, as it spins, generates a perpendicular magnetic field. Now, if I radiate any sample has this, each and every proton, each and every electron has a zero magnetic field. Okay. Magnetic fields have like a north and a south, and they align with each other, right? Now, let's say that this is my sample here in the middle. Your typical NMR has this humongous magnet. Look, they look typically like silos, okay? And you come in with your sample in this little test tube, and kind of go on top and drop this in the middle of this silo. Now, the silo is this humongous magnet, very, very powerful magnet. What you're dropping inside is your sample that has this magnetic field, right? Compared to the outside magnet, it's really, really small millionth of a gas. But the net magnetic field of your sample can either align itself with the outside magnet, north to south, or against. In other words, if you're playing with Thomas the Tank Engine little trains, you ever do that? And they have magnets at the end, and you try to put them together, and either they stick the magnets, or they kind of repel each other, and you cannot stick them, okay? Because there's a north and a south to a magnet. You cannot put two norths together, they repel each other. You need to put north with south, like plus with minus, okay? So, when your north is aligned to with your south on the outside magnet, that is a lower energy environment. That is the way it wants to be. If I try to put south with south, it's going to be a higher energy. I need to kind of like push them together to go together. So there's two energy levels here. A lower energy level and a higher energy level. A lower energy level in which the net magnetic field of my sample is aligned properly with the outside magnetic field. And a higher energy in which this is against the outside magnetic field. The amount of energy needed to go from the low to the high magnetic field is that radio frequency that I'm going to irradiate my sample with. You don't need a whole lot of energy to get that proton to flip. In other words, rather than be spinning like this and have a magnetic field like this, flip it and have it spin like this, or something like this, and have a magnetic field like that. Okay? It's just the direction of the spin changes. So that is what we are recording. That those protons absorbing this radio frequency, flipping, spinning in the opposite direction, and now changing how those magnetic fields are aligned with each other. As usual, what we measure is the absorption. Okay, how much of this energy is being absorbed, and then we come up with an absorption spectrum. Okay, I promise I will not look at any equations or anything like that. You can ignore that. I just want to know, given a spectrum, can you figure out what is the compound? That's it. Don't worry about all this and field strengths and Gausses and stuff like that. Okay. Now, first we're going to look at proton and ammonia. Just the proton, the hydrogens in a molecule, nothing else. Now, depending on the environment of these hydrogens, meaning what they're connected to, they're going to absorb that radio frequency, different radio frequencies. Okay? So if I have hydrogens attached to an sp3 carbon in an alkane type environment, they're going to absorb at a certain radio frequency, different than if you have a hydrogen attached to a much more electronegative atom like oxygen. So depending on what they're attached to, they are going to absorb different radio frequencies, and I'm going to be able to see different absorptions. You clear on that? Okay, so this is just showing you an NMR. I drop my sample inside the big magnet. I irradiate with a radio frequency. My sample absorbs at certain specific frequencies, which is detected by a detector, and I end up with a spectrum at the end of the day. Okay, now, let me show you an NMR. So we're talking here about methanol. Methanol has 3 identical hydrogens connected to an sp3 carbon, which is connected to an oxygen, and 1 different hydrogen connected directly to oxygen. So these are going to absorb in 2 different places and 2 different frequencies. Okay? Now, this right here is tetramethylsilane. Tetramethylsilane is this molecule. Silicon is a very non-electronegative atom. So, and all 12 of these hydrogens are identical. It would be very, very difficult to find an environment where these hydrogens are attached to something that is less electronegative. So, hydrogens that are attached to less electronegative stuff show up on this end. Hydrogens that are attached to more electronegative stuff, like oxygen, show further to the left. We talk about upfield and downfield. So, you would expect this hydrogen connected to oxygen to be this one further downfield, while these attached to carbon, less electronegative, to be this. And all these hydrogens that has sp3 carbon attached to silicon are showing right here. Why is tetramethylsilane showing, for any sample that you make, you add a drop of tetramethylsilane. And then in your spectrum, define this as 0. And everything else is relative to 0. This is your calibration. Let's force this to read 0, and then everything else is relative to that. So it's like an internal standard that you're adding. Okay? That's not part of your sample. These are the peaks that you need to look at. Now, the numbers that you're going to see in here, whatever those numbers happen to be, is we read them in parts per million. We call it the delta scale. I'll talk in a second about what is a delta scale. But typically this goes from 0 to about 10-ish or so. So where this falls relative to these numbers, no, this is at whatever. No, this is really wrong. So I'll change that. These would probably be showing at around 2-ish. And these, who knows? OHs, anything that a hydrogen bond is always a mystery. But, let's say something there. So, we call this your chemical shift. Your chemical shift gives you an idea of the environment of that proton. This proton, this hydrogen, is connected to what type of atom or functional group. Okay, that's what the chemical shift tells you. Am I connected to oxygen? Am I connected to an sp3 carbon? Am I connected to an sp2 carbon? That's what the chemical shift tells you. Now, in addition to that, notice that these peaks are of different height. The height of the peak, or more specifically, the area under the peak, is directly proportional to the number of hydrogens that correspond to that absorption. And often we use what we call an integral trace. So when you integrate this, you're going to have like a trace that goes flat. And then let's say this goes up like this. And then this goes up 1, 2, 3. Let's say like that. So when you look at the height that this trace goes up because of this peak, and then at this height, you're going to see that this is 3 times bigger than this. So that, again, the integration, remember calculus, you have something and you can integrate the area under that curve. So that's what we're doing. We're integrating the area under the curve, and this shows up as a height. So if this is 3 times larger than this, that's because in here we have 3 hydrogens versus 1 hydrogen. Okay? So the chemical shift is telling you what these hydrogens are attached to. The area under the peak is telling you how many of each type of hydrogen do I have. Okay? Now, there's going to be something else that we're not seeing in here, but we'll see later, which is called multiplicity. And multiplicity tells you if I have a hydrogen here and a hydrogen here, how are these two interacting together? So it's in essence telling me connectivity. What's in the carbon next door? Okay. So that's a third thing that we're going to be looking at. Okay. All right. So again, your chemical shift is measured in parts per million. It's relative to tetramethylsilane, which we define as 0. Now, we said that we drop the sample inside a magnet. There's different strengths for my magnets. I could have 60 megahertz, 90 megahertz, 500 megahertz, 900 megahertz. 500 megahertz, maybe $500,000. 900 megahertz, upwards of $1 million. 60 megahertz, for different magnets. Now, the stronger the magnet, the more resolution you have, the more you can see. Okay? One is a blob, the other one gives you a lot of definition. That kind of depends on your budget. But at the end of the day, I would like my chemical shift to always be the same. If this is coming at, let's say, chemical shift 3, granted one will give me a blob and one will give me nice definition, but I would always like it to be on 3 and not be meandering all over the place. Okay? So, since the magnets change, the absolute frequency at which I irradiate also changes. But the delta scale is always the same, because whatever the shift is downfield from TMS, I'm going to divide by the total frequency. So, because I'm dividing by the same number, the ratio is always the same. So, in here, let's say I have whatever divided by whatever gives me 1, a much higher number divided by a higher number still gives me 1. So regardless of the strength of the magnet that you're using, the chemical shift for the same type of hydrogen in the same environment is always going to be the same. Okay? So again, hydrogens in a methyl group attached to oxygen, I can expect to come at about a chemical shift of 3.5. And it's always going to be the case. All right. Okay, so let's start looking at some of these chemical shifts, regardless of the magnetism. So, remember, if the more electronegative the group that the hydrogen is attached to, the more downfield you're going to be, the higher the chemical shifts. So, here we have hydrogens attached to an sp3 carbon, no electronegative groups. My chemical shift is less, well, close to 0 at that point. Okay. Now, everything else is the same except I could have replaced this hydrogen with a chlorine. Clearly, this is more electronegative. So, the signal for these hydrogens, we're only looking at proton NMR here. So we're only looking at hydrogen. But because this chlorine is sucking electron density away from these hydrogens are more positive, they're more de-shielded. It's electrons, the shield of electrons has kind of gone away. And more de-shielded comes further downfield. So again, if you're looking at an NMR where this is 0 TMS, and let's say this is 10, this is downfield de-shielded. The protons are de-shielded, the electrons have been sucked away. These protons upfield are more shielded. They have a little core of electrons around that are shielding the nucleus from whatever radio frequency is coming in. Okay? So now, my chemical shift is down to 3, from 0.2 to 3. That's a huge change. Okay, let's add 2 chlorines and look at these hydrogens. Now my chemical shift is down to 5.3. Let's add 3 chlorines and look at this hydrogen. Now my chemical shift is down to 7.2. So for each additional chlorine that I add, roughly my chemical shift has gone downfield by 2 ppm, 2 parts per million. Sometimes a little bit more, a little bit less, but it's a big jump by virtue of the fact that you're adding those chlorines and those protons are progressively more de-shielded. Okay? So, let's look at some other chemical shifts. You will have this table, exactly this table, in an exam. be spending all your time looking at this table. You're not going to have time to look at the actual spectrum and the actual interactions in there. It is really helpful to have a good general idea of these chemical shifts. And if you specifically, I need to make sure of this, okay, we'll look at it. But you should start learning some of these chemical shifts if you want to be effective at doing it among problems. Okay, so your typical alkane environment. Hydrogens attached to an sp3 carbon. You can expect to come roughly around 1. Now, if this is a primary carbon, then slightly less than 1. As we add more carbons, right, we're looking at the hydrogens that are attached to this carbon that is attached, in this case, to only 1 carbon, in this case, to 2 carbons. So those carbons are sucking more electron density, so my chemical shift is down to about 1.3. And add 3 carbons, and now maybe 1.4. But roughly, if you're a hydrogen attached to an sp3 carbon, roughly, you can expect that to show up around 1 with small differences if you are primary, secondary, or tertiary. Okay. Now, if you are, this assumes more sp3 carbons. If this hydrogen is attached to an sp3 carbon that is attached to a carbonyl, now this is coming at around 2. Because of course, this sucks electron density away, making this more positive, sucking electron density away, de-shielding these protons. Okay. Now, a hydrogen attached to an sp carbon comes at about 2.5. A hydrogen attached to an sp3 carbon attached to a heteroatom. Now, this heteroatom could be a halogen, it could be a nitrogen, it could be an oxygen, a bromine, one of those things, right? Which of these is the most electronegative? The oxygen. So, these hydrogens here would come further downfield if this CH2, let's say, is attached to an oxygen. In this window, 3 to 4, the 4 would more likely be the CH2 attached to oxygen, with this maybe a 3.5 or 3.2, or maybe a 3, somewhere in there, this would be lower, this would be higher. But it depends on what else is there, okay? But that's that window between 3 and 4, which can extend a little bit, maybe 4.2, somewhere in there. Okay, we said that if a hydrogen is attached to an sp carbon, that comes at 2.5. Very different than if a hydrogen is attached to an sp2 carbon, where now it comes between 5 and 6. We'll talk about why the big difference there. So alkane environment, a hydrogen attached to an sp3 carbon. In an alkane environment, about 1. A hydrogen attached to an sp carbon at about 2.5. Attached directly to an sp2 carbon between 5 and 6. That's a hydrogen attached to an sp2 carbon. But if you're a hydrogen attached to an sp3 carbon, which is attached to an sp2 carbon, now we're coming at a more alkane environment, a little bit more because this is an sp. A hydrogen directly attached to a benzene. This is your typical aromatic region. Therefore, between 7 and 7.5. Those are aromatic hydrogens, almost all. Okay. In the same way that with IR, remember you recognize a benzene ring because you have that CC stretch at 1600, there's overtones, right? And then at about 3100, you have the unsaturated CH stretch, and all of that was typical of a benzene ring. Well, in proton NMR, when you have absorptions at between 7 and 7.5, that talks about the hydrogens that are attached to a benzene ring. Okay. This is directly attached to a benzene ring. These are not directly attached to a benzene ring. These are attached to a carbon, an sp3 carbon, which then is attached to a benzene ring. These come a lot lower at about 2 to 2.5. If you have a hydrogen attached to an sp2 carbon that is attached to an oxygen, which is sucking electron density away, putting a lot of positive charge here, this is very downfield between 9 and 10. And even more so, if you're attached, if you're part of a carboxylic acid. Now, with all this resonance and this being attached to an oxygen, this is coming 11, 12, 13. That's the hydrogen in a carboxylic acid. By an OH, not attached to a carbonyl, but attached to a regular carbon, sp3 carbon, this kind of hydrogen bonds. So anything that hydrogen bonds, you have a variety of different absorptions, because as that hydrogen bond and molecules move closer or further apart, changes. So these type of things tend to be more, rather than sharp peaks, they tend to be more like blobs. Somewhere between 2 and 5. That really varies. And again, things that have hydrogen bond, you tend to fluctuate a little. All right, so let's look at problem 1. So this is what we use to talk about proton NMR. Proton, we're talking about this isotope of hydrogen. 1 proton, 0 neutrons, the most common isotope of hydrogen. Okay, that's the type of proton that we're looking at. Oh, by the way, not all atoms are what we call NMR active, absorbed in NMR. In order for an atom to absorb NMR, we need an odd mass number. Which is fine, because this is by far the most abundant isotope of hydrogen. But this is not the most abundant isotope of carbon. Carbon-12, the most abundant, 89.9% of the sample, is invisible to NMR. This, of which we have at 1% only, 99+% of this, 1% of this. This is the only one that is NMR active. So, while this is a piece of cake to get, and I get strong signals running this for 30 seconds, this I could be overnight trying to acquire enough signal, because there's so few carbon-13s in that sample. Okay? So, there's 8 gazillion proton NMRs floating around, a lot less carbon, because it's a lot more difficult to obtain. Okay? It's not a question of what is more important or whatever. It's just that I can run 800 proton NMRs in the time that it takes me to run 1 carbon. So it's easier to do this. I can run during my lunch break and run a whole bunch of these. I need to reserve the instrument for a whole night to get this one. Okay, so there's a difference. Okay, but we'll get to carbon-13 in a while. For now, let's go back to my proton NMR. So, here's this molecule: cyclohexane, acetone, benzene, dichloromethane, trimethylamine, and this dialdehyde glyoxide. Now, I've carefully given you molecules. I've carefully given you molecules that are perfectly symmetrical, so that all the hydrogens in each of these molecules are identical, and each of these molecules will only give you one peak, one absorption, because all the hydrogens in that molecule absorb at the same rate. Okay? Of course, we're going to get to look at molecules that absorb at different frequencies. But let's try to see whether it's this hydrogen, or this one, or this one, or this one, or any of the 12 hydrogens in this molecule. Where would you expect any one of the 12 hydrogens in cyclohexane to absorb?
(1.3).
Right. Those hydrogens are attached to an sp3, a secondary sp3 carbon. So, about 1.3. This delta is like that, or sometimes you may see 1.3 ppm. Those are the units, parts per million. But this is telling you on the delta scale it comes at 1.3. There's different ways of calculating those signals. Okay, now any one of these 6 hydrogens in acetone, which are all identical, where would you expect that to come?
2.1.
About 2.4, right? Any of these 6 hydrogens in benzene, roughly about 7.2, give or take half, it depends on the rest of the environment. About any one of these 2 hydrogens.
5.3.
If you are attached to one chlorine, you would expect to be coming on the lower end here. But from an alkane to adding 1 chlorine, the difference is about 2 ppms. Add a second chlorine, and I should expect this to be at around 5. And we saw that before, and when you add 2 chlorines, about 5. So I can make this myself and look at how, 1 is this much, relative to an alkane, a second is this much more, and so on and so forth. So, around 5. I put 5.3 because we know exactly, but around 5 is where I would expect that to show up. Okay, how about any one of these 9 hydrogens? We have methyl groups attached to nitrogen, right? Probably on the lower end of this range, or maybe halfway up, somewhere between 3 and 3.5. Somewhere there. How about any one of these 2 hydrogens? This is an aldehyde. it comes between 9 and 10 hydrogens in an hour. Nothing else shows there. The same as nothing else shows between 10 and 12 except the hydrogen and carboxylic acid. If you can start learning some of these, it's gonna make interpreting spectra a lot simpler. You will have this table, but it really takes off to start learning some of these.